Today we're going to look at the fundamental theorem of algebra. What the fundamental theorem of algebra allows us to do is to solve a polynomial that's not factorable and that has rational roots. So let's go ahead and look at an example of a polynomial that's not factorable. So we have x to the third plus x squared minus x plus 2 equals 0. In order to find the zeros of this up to this point, we would factor it. If I look at the factorization of this though, since we have 4 terms, we would factor by grouping. I pull out an x squared, I'm left with x plus 1. Here I pull out the negative 1, so I'm left with x minus 2 equal to 0. Notice I don't have a common factor in either of these two terms, so it's not factorable. So we bring in the fundamental theorem of algebra. What it tells us to do is to find the p-values. And the p-values are simply taking the constant term and looking at the factors of them. So looking at the factors of the constant. Well, if I have positive 2, my factors, I can have plus or minus 1, and I have plus or minus 2. Remember, a factor is a number that will divide evenly into that number that we're looking at. And we can have the positive or the negative for 2. I'm also going to look at the q values, and the q values are equal to the factors of the leading coefficient. Our leading coefficient, remember, is a term that comes first, and it's the number that's in front of that variable. In this case, we have 1. All the factors of 1 are simply plus or minus 1. Now what we're going to do is take the p-values, so the factors of the constant, and divide them by the q-values, or the factors of the leading coefficient. If I take plus or minus 1 and divide it by a positive or negative 1, I'll end up with a positive or negative 1. Same thing with a 2. If I take positive or negative 2 and divide it by positive or negative 1, I'll end up with positive or negative 2. What the fundamental theorem of algebra tells us is that if this has rational roots, then one of them will be a p divided by q. So at this point what we can do is take these factors, we have 4 of them, positive 1, negative 1, positive 2, negative 2, and find a 0 for this. There's a couple ways you can do that. 1 would be simply to plug in those values, or 2, use synthetic division. Synthetic division will allow us to get to the answer a little quicker in the end. So let's go ahead and start with our synthetic division. We're going to start with a positive 1. Remember, synthetic division, we're going to take the coefficients of each of our terms. So we have 1, 1, negative 1, and 2. I'm going to go ahead and bring down my first term. I'm going to multiply the boxed number to the bottom on the number on the bottom. I'm going to bring it to the top. I'm going to add down, do the process again. 1 times 2 is 2, add down. 1 times 1 is 1, add down. Remember, for this to be a factor or a 0, our remainder has to be 0. In this case, we get 3 out. So 1 is not going to work for us. Let's go ahead and skip ahead and look at negative 2. If I plug in negative 2, I get 1, 1, negative 1, 2 as my coefficients. Bring down my 1. Negative 2 times 1 gives me negative 2. Add down, I get negative 1, 2, 1, negative 2, 0. Notice here my remainder is a 0, so we say that negative 2 is a 0 of this function, or gives me a 0 out. So that tells us that x equals negative 2. We can also go ahead and look at the remaining polynomial. Remember, this polynomial would give us as x squared minus x plus 1. if I set that equal to 0, I can go ahead and solve this equation using the quadratic formula. Remember, the quadratic formula tells us negative b, so 1 plus or minus the square root b squared, which is 1, minus 4 times a times c, which is 4, all over 2 times a. Simplifying this, I have 1 plus or minus the square root of negative 3 over 2. And simplifying your square root of negative 3 gives us 1 plus or minus I radical 3 divided by 2. And there's my other two solutions. So x equals negative 2 and x equals 1 plus or minus I radical 3 over 2. And that's an example of solving a polynomial that's not factorable. Let's go ahead and take another example. Example 2. And let's look at x to the third minus 5x squared plus 7x minus 35 equal to 0. Now I know this one is factorable, but for the case of being able to solve using the fundamental theorem of algebra, let's go ahead and look at our p and q values. Here are p values. Remember to take the constant term and all the factors of it. So the factors of negative 35 are plus or minus 1, plus or minus 5, plus or minus 7, and plus or minus 35. Our q value, in this case, our leading coefficient, are plus or minus 1. Again, the nice thing with this one is that all of our p values divided by the q value will simply be the p values. We're going to go ahead and find a 0. In order to find a 0 here, we're going to use our synthetic division. If I plug in 1, using my coefficients, I have 1, negative 5, 7, and negative 35. I have 1, 1, negative 4, negative 4, 3, 3. I know that's not going to be 0, so that we know that this is not a 0 of our function. Skipping ahead again, I'm going to try 5. I have 1, negative 5, 7, negative 35. Bring down my 1. 5 times 1 is 5. Here I get 0. 5 times 0 is 0. Add down, I get 7. 5 times 7 is 35. So I get 0. Since my remainder is 0, I know that 5 is a solution to this function, or this equation. So x equals 5. My remaining information is x squared plus 7. Remember, I have 0 x's here, and 0 x's is nothing, so I get x squared plus 7 equal to 0. Solving this one, I don't need the quadratic formula since I don't have that linear term or middle term, so I can go ahead and use my square root method. Square root method tells me to go ahead and solve for that x squared, so subtract 7 from both sides, and then take the square root of both sides. So I get x equals plus or minus, cleaning up the square root of negative 7, I get I radical 7. So my solutions are x equals plus or minus I radical 7 and x equals 5. And there's two examples of using the fundamental theorem of algebra to solve cubic equations.